Okay, relativity are discussing. Okay, so today we'll discuss relativistic mechanics. We'll discuss relativistic mechanics. മുൻപത്തെ ക്ലാസ്സുകൾ അറ്റൻഡ് ചെയ്തിട്ടുണ്ടോ?
ഇന്നലത്തെ ക്ലാസ് അറ്റൻഡ് ചെയ്തിട്ടുണ്ട്.
ഓക്കെ,
2 ദിവസം അറ്റൻഡ് ചെയ്തിട്ടുണ്ട്. ഞാൻ വീഡിയോസ് കാണാറുണ്ട് സർ.
ഓക്കെ, അപ്പൊ എന്തെങ്കിലും ഡൗട്ട് ഉണ്ടെങ്കിൽ ചോദിച്ചാൽ മതി, നമുക്ക് ക്ലിയർ ചെയ്യാം. Relativistic mechanics. So far we were discussing, I'll just summarize some of the things. Okay, we said that the geometry of space-time is like this: d square is equal to c square dt square minus, you can write it as dx vector square, all right, because x vector square means this. Okay, dx vector square means this: dx vector dot dx vector. Okay, that's equal to dx square plus dy square plus dz square, right? That's one way. Or we can write dr square. Okay, if you like, you can write it as dr square. Okay, so we said that this is the time separation between the events. So this is the interval between two events in space-time, right? It takes space-time, there are two events, you are calculating ds square. Okay, so this is the time separation, and this is the spatial separation between the events, all right? This is what do you say, dx, and this is c dt, right? So in this situation, this is what we call as the invariant interval. And we said this is Lorentz invariant quantity. This is Lorentz invariant, that's why we call it as the invariant interval. All right, if you go from one frame to frame, it doesn't change. And we also said that this is related to the proper time by this relation. Okay, d square is equal to c square d tau square. Okay, this is the proper time between the events, proper time interval between the events. So what do you mean by the proper time interval between these two events? It's the time registered on a clock that you take from event 1 to event 2. Right, if you take a clock from event 1 to event 2 in space time, right, the time shown on that clock would be the proper time. Okay, and we know that this proper time also is obtained in this form: d tau is equal to dt square root of 1 minus v square by c square. You can get it from here, or we already know this because we have learned what we call as the relativistic time dilation, right? And this we called as a proper time. This is the same we call as the proper time, and we denote it as d tau, that's all. Okay, so you see that d tau is equal to dt square root of 1 minus v square by c square. Okay, now, right, we defined vectors, 4 vectors. We defined 4 vectors. Okay, so 4 vectors are a collection of 4 numbers, okay, set of 4 numbers which transform in this way under the Lorentz transformations, where this is the Lorentz transformation matrix. Okay, these things we discussed. And any collection of 4 numbers, these are 4 numbers: a0, a1, a2, a3. Okay. Any collection of 4 numbers. Okay, in the notes I have put small a, doesn't matter. Okay, lambda, mu prime, nu, x nu. This is a matrix. Remember that this is a matrix. Okay, so these are 4 vectors, right? And as the simplest example for a 4 vector is the what do you say, the coordinate, right? This x mu, x mu. Okay? And we'll denote 4 vectors simply by a letter. Okay, in contrast to 3 vectors, we'll always put a vector sign on top of it. Right, we'll put a vector sign for a 3 vector, and for a 4 vector we'll write simply a. Okay, and the components we can write like this: a, okay, this is the 4 vector. The components we write it as a mu. There are 4 components. Okay, and these are a0 and a vector. All right, this a vector is a short notation. You can write it also as a0 comma ai, where in our notation we use this Latin indices only for the spatial part, not for the time part. Time part is always 0. Okay, so much we said. And then we define the scalar product. Scalar product, we know that scalar product has to be invariant, and taking a hint from this fact that this is invariant, we know that the scalar product has to be of this form. We said a dot b has to be equal to, we say it is a0 b0 minus a vector dot b vector. Okay, where a vector dot b vector are the corresponding 3 vectors. So this is, or we can write it as we also wrote it as A0, B0 minus A1, B1 minus A2, B2 minus A3, B3. Okay, 0 is the time component, temporal part of the vector, of the temporal component, it's called. And A1 is like AX, the X component, Y component, and Z component. If you look at this part, it is simply A vector dot B vector with the minus sign here. Okay, and we said we can write this as a metric because we usually write if you have two vectors. All right, I'm using the same letter, but I'm using three vectors. If you have two vectors in Euclidean space, okay, these are three vectors, these are four vectors. Okay, we said we can write it as AI, Bj, delta Ij, where delta Ij is the Kronecker delta. We called it the metric of Euclidean space. Metric of Euclidean space. Similarly, we can introduce a metric here to take care of this minus sign. We said we can write A dot B as A mu, B nu, eta mu nu. All right, eta mu nu we call the metric of Minkowski space or metric of space time. Right, and it has two indices. We can write it as a matrix. Okay, metric means it tells you how to measure a length in a given geometry. Right, it tells us how to measure length between 2 points in a given geometry. That's why it's called metric. Okay, so if it's a flat space, you can just measure the length using the usual Pythagoras theorem, and delta Ij here will take care of that. If it's on the surface of a sphere, you will have to use dr square is equal to if it's on the surface of a sphere, okay, the length between 2 points, we write it like dr square plus r square d theta square plus r square sine square theta d phi square. Am I right? Okay, on the surface of a sphere, right? And the metric here is metric. Okay, I'll write it as Gij, for example. Gij, the metric here is 1, 0, 0, 0, r square, 0, 0, 0, r square, sine square theta. This is what we mean by metric, because these coefficients here, right, the coefficients of this coordinate differential square, or the difference in coordinate square, tells us how to measure the distance. Okay, how to combine these infinitesimal displacements, infinitesimal differences in such a way that you get a distance between 2 points. Okay, that's what we call as the metric, and this is the metric for Minkowski space. All right, this tells us how to obtain a notion of distance between 2 points. In this case, it's two events in space-time. Okay, and we said that eta mu nu. In order to get minus signs here and plus sign for time part, we say eta mu nu will be 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, 0, and 0, 0, 0, minus 1. Okay, there are minus signs. There is a relative minus sign between the time part and the space part. Okay, just like we have here. Right now, there is another. So this how we use this invariant interval. Okay, I'll just so ds square, the invariant interval now can be written as a scalar product. Dx mu eta mu nu. All right, this is one way to write the scalar product. Okay. Then we talked about the raising and lowering of indices. Raising and lowering of indices. Am I right? So raising and lowering of indexes. So this thing, a dot b is equal to a mu, b mu, eta mu nu. Okay, we can write b nu eta mu nu. Okay, this mu is summed over, repeated indices are summed over. So there is actually just one index left. All right. So this we define as an object with a lower index, and we call this as the covector or one form. Okay, components of covector or one form. It's also called the components of the covariant vector. Covariant vector. This term covariant vector is a bit outdated, but still in some of the textbooks they use it. Okay. In contrast, this with the upper index they call a vector. This is simply a vector, components of a vector. Okay. It's also called a contravariant vector. Okay. It's also called a contravariant vector. Okay. So if you have the scalar product of two vectors, you know that it's Lorentz invariant. Or this is one way to construct Lorentz invariant quantities. You just take the scalar product between two vectors, all right, and you get a Lorentz invariant quantity. It doesn't matter what the components are. Okay, in different coordinate system, these components will be different. Okay, in different coordinate system, these components will be different. These numbers will be different, but the combination, the scalar product of vectors is always invariant. All right, so this we can write it as simply A mu B mu. Okay, this you can also write, you can combine also these two things. Okay, you can also combine these two things. This mu will be summed over. You can also write it as A nu B nu. Right, now this mu is known as a dummy index. Here mu and nu are known as a dummy index. These are known as dummy indices. All right, so because we are repeating it, the meaning of using mu twice is this: it's a prescription to sum over. Okay, if you see something like this means this is a0 b0 plus a1 b1 plus a2 b2 plus a3 b3. All right, so this repeated index is just a prescription to sum over. That's why it's called a dummy index. Okay, so it doesn't matter if you change two dummy index at the same time. Okay, we have got mu here. It's okay if you write alpha and alpha because it's the same thing. Okay, if you expand this also, you again get a0 b0 plus a1 b1 plus a2 b2 plus a3 b3. All right, and the metric tells us that b1 equal to minus of b1. Okay, b2 equal to minus of b2 and b3 equal to minus of b3. Okay, so which means that when you lower the index, all right, when you lower the index, the space part gets an extra minus sign, whereas the time part remains the same. B0 is equal to B0 because eta 0 is plus 1 and eta 1 eta 2 eta 3 are equal to minus 1. That's why we get a minus sign for the spatial part when we lower the index. Okay. Or generally we can write it like this because we use Latin indices for the spatial part. We can simply write it like this: bi, okay, is equal to minus of bi. All right. Okay. There's one more detail we talked about. So we can write d square is equal to simply dx mu. Okay, this is one way of writing the invariant interval, and we again see that this is invariant because you can write it as a scalar product, and scalar product is Lorentz invariant. You again see that this interval that we constructed is Lorentz invariant because scalar products are Lorentz invariant. Okay, it's just like in rotation. In rotation, you know that the three vector, a vector dot b vector, these quantities are invariant under rotations. In the same way, this construction, these quantities, what we call as a scalar product or a four-dimensional scalar product, is Lorentz invariant. Okay. Now we discussed time-like vectors. Time-like interval. Okay, space-like interval. And light-like interval. Am I right? Light-like interval. Okay. So in the notation that we used, all right, this was if d square is greater than 0. Okay, because we wrote it as c square dt square minus dx square. So if c square dt, if the time part is dominating, we say that it is a time-like. All right. If space part is dominating, we'll have d square is less than 0. In this case, c dt will be less than dx. Okay, and those okay. So then this is known as space-like. Okay, can you hear me?
Sir, അതൊന്നും കൂടെ ഒന്ന് പറയോ?
ഏതാണ്?
ഇപ്പൊ പറഞ്ഞതൊന്നും കൂടെ പറയോ?
Time-like, space-like.
Time-like interval d square.
Okay, I'll just okay. This
d square greater than 0.
Yeah, d square greater than 0. When d square is greater than 0, this means that c square dt square, c square dt square minus dx square. Am I right? I'm just writing one index. Okay, I'm just writing one dimension, one spatial dimension. We can write three spatial dimensions, doesn't matter. Or we can include all these three dr vector square. Okay, this is greater than 0. This means that c dt is greater than dr. Am I right? The modulus, I'll write it like this. Okay. This means that the time separation between the events is greater than the space separation. Am I right? Because this term dominates. It's a minus and you get a positive thing. So that means the time separation part dominates. Am I right? Are you followed? Yeah. So that's why we say that this is time-like interval. Okay. In similar manner, if this part is dominating, then this ds square would be negative, right? Then we say it's space-like interval because it's this part is dominating now, right? This spatial separation is greater than what you call as a temporal separation, all right? With a c square there, that c square has to be there because you need the same unit system. Is this clear? And since we have minus sign, since we have minus sign here, we have something new. D square can be equal to 0 also. Okay, this is light-like interval. Okay, null interval. It's also called the null interval. In this case, c square dt square is equal to dr vector square. This means that the events have exactly the separation that can be covered by a light signal. All right, if you look at this, you see c square is equal to dr square by dt square, or c is equal to dr by modulus. Okay, that's modulus divided by dt. This is the speed of light. Okay, so if the events are separated in such a way that a light signal from event E1 will pass through event E2, then we say they are light-like separated. Right? If it's outside, then it means that light signal, not even light signal, can pass between these two events. Then they are separated space-like. Okay, I'll just write it. This is E2. I'll write it as E3. This is E4. Okay, these are three events. All right, this is E1. Now, event E2 can be reached from event E1 by a light signal. Okay, according to this. Then we say that the interval between them is light-like. Okay, but now not even light can reach E3. Then we say that the separation is space-like. Now, if you go at a lower velocity than speed of light, you can reach E4. So these are time-like. Okay, E4 and E1 are time-like separated. E2 and E1 are light-like separated. E1 and E3 are space-like separated. All right, because this is the maximum speed. This is the maximum speed that you can travel from E1. All right, the inclination of the world line cannot exceed this. Right, because the inclination of the world line will tell you what the speed is. All right, and you cannot exceed the speed of light. Right? So there's no way you can reach E1, E3 from E1. Right, and we can complete this, and we called it as the light cone. So events inside the light cone are space time-like separated from E1. Events outside the light cone are space-like separated, and events on the light cone, right, on these lines are called light-like separated. Right, so we said this, but we can generalize this to vectors. Okay, since we have d square can be written as a scalar product. Okay, since d square can be written as a scalar product, right, we can just generalize this notion for vectors. Okay, so we'll have, in the same way, we can generalize this. We'll have time-like vectors, space-like vectors, and light-like vectors, All right, so we define it in terms of the scalar product. Okay, we have got, if time-like vectors is a mu, or a dot a is greater than 0. Okay, just like here, because this is dx mu. All right, so space-like vectors, if a mu, this is also written as a dot a, or we can write as a square, doesn't matter, is less than 0, then we say this vector is space-like, and if a mu is equal to 0, we say that it is light-like. Is this clear? So when we say a time-like vector, it means that the scalar product with itself is greater than 0. Okay. All right. These things we may be using this, or some question can be asked. Okay, using these terms. Okay, so it's good to know this. All right. So it's light-like vectors. Okay. Is this clear? So this is a summary of what we already.
Yes, sir.
This is a summary of what we already discussed. Also, this space-like, light-like, and time-like vectors we have introduced. Okay. Okay. Now, one point I want you to remember is that, okay, so we wanted to construct a quantity that is Lorentz invariant, and we took it as d square equal to c square dt square minus dx square. Right, in most particle physics books, I think this is the convention we use. Okay, But since this is invariant, this is also invariant. All right, ds square is equal to minus c square dt square plus dx square. Okay, so you could take this as the invariant interval or this, it doesn't matter. Okay, if you take it this, then the proper time will be related to this by minus d square by c square. All right, and then here the signs will change. You'll have a time like vector if it's less than 0. All right, if it's minus here, you see it's minus and plus here. Okay. So this is known as giving the metric. They may use this convention or this convention. Both are possible. Right. So if you use this convention, then proper time d tau square is minus d square by c square. Okay, and for time like vectors you will have less than 0. For space like vector you will have greater than 0. For light like it's the same. Is this clear? So you, if this is given, if the metric, this is known as a metric or the invariant interval, if the interval is given, you have to be careful. In this case the metric will be written as, all right, in this case the metric would be, you would have a minus 1 here and 0 1 0 0 0 0 1 0 0 0 0 1. All right. So in this case, when you lower the index, the time part will get a minus sign and the space part will remain the same if this is the convention you are using. Okay, so you have to remember this. So whichever convention the question, in whichever convention the question is given, you have to follow that convention. It doesn't really matter. All right, I am just choosing one of the conventions. If you take Griffith, for example, all right, if you take electrodynamics by Griffiths, there was a nice chapter on relativity and electrodynamics. Okay. Something like that. Right? So in that he uses the opposite convention, minus c square dt square. He takes ds square as minus c square dt square plus dx square. In this case, he says ds square. So he calls, if you take this as the convention, this as the metric, then if mu is less than 0, it is time like. If mu is greater than 0, it's space like. Okay, and the other thing. Okay. So this you have to keep in mind. There is no need for confusion here, okay? Because both are correct. Even in the same problem, we can use both conventions. The only important thing is that if you have an equation A equal to B, you should use the same convention on both sides of the equation. That's only thing you need to do. You need to be careful about. Okay. So even if you do use two different conventions in the same problem, you won't make a mistake if you are using the same convention on both sides of a given equation, right? But it's a good practice to fix your notation first so that you don't confuse between them. You fix your notation first and then do the problem. Okay. Now, so for example, if they ask for a proper time, okay, if you are using this convention, you can simply calculate ds square and divide it by c square, you'll get the proper time. Right? If you are using this convention, you'll have to find ds square and multiply it with a minus sign and then divide it by c square. All right. So that's the only thing you need to be careful about. And even in some of the problems, we can use these conventions, different conventions. For example, when I used the length contraction, right, it was convenient to use d square equal to dx square minus c square dt square. If you might have noticed, okay. So you just have to be careful. The only thing is that this means if it's time like that, means the time part has to dominate the space part, right? The time part has to dominate the space part. This has to be greater. Okay. Now, if you are using this convention, then if time part is greater than the space part, then you will have a minus sign here. That's all. Is that clear?
Yes.
Okay. All right. So that's not. We didn't discuss anything too much new in these things. We'll go to relativistic mechanics now. We have enough material to go to relativistic mechanics. Okay. So we know that dx mu transforms like a vector. This is a 4 vector, right? I mean, when mu comes, these are 4 components. So these are 4 vectors. So this is a vector. All right. Now we have a 4 vector for displacement, for example. This is a displacement 4 vector, if you like. All right. The infinitesimal displacement 4 vector. Okay. So do we have a 4 vector for velocity? Okay. Can we construct a quantity that we can call a 4 velocity? Can we call something a 4 velocity? Okay. The obvious choice that comes to our mind is dx mu by dt. Okay. Can we call this a 4 velocity? Now, if this has to be called a 4 velocity, this must transform under Lorentz transformation just like a vector. Okay. But you will see that dx mu, the numerator already transforms like a vector under Lorentz transformation, but dt has a non-trivial transformation. dt also transforms under Lorentz transformation. So this whole quantity does not transform as a vector. Okay, so now what we can do is to construct the for velocity in this way. Eta mu, we call it as eta mu, is dx mu by d tau. Instead of dt, we use a proper time here. Okay, now since proper time is relativistically invariant, okay, since the proper time is relativistically invariant, this whole quantity transforms just like a vector, because dx mu transforms like a vector, right? Dx mu already transforms like a vector, d tau is invariant. Okay, this already transforms like a vector, so it's easy to show that eta mu itself transforms as a vector. In other words, eta mu prime is equal to lambda mu prime mu eta mu. Okay, this transformation rule is satisfied. Okay, because this is the Lorentz transformation matrix. This Lorentz transformation matrix could be a boost along the x direction, or boost along the y direction, or boost along some arbitrary direction. It doesn't matter. You always you know how to construct the Lorentz transformation matrix. All right, we already have seen the example for that using cos h5, sin h5, and all that. Okay, so this is known as the for velocity. For velocity. Okay, now let's look at the components of this for velocity. Let's look at the components of this for velocity. Eta mu, the components we can write eta 0 comma eta vector in a way. Okay, and what's eta 0? You just use this. Okay, or you can write it as eta I if you like. I think it's better to, you should be familiar with both this notation. Okay, we can also write it as eta 0 comma eta I. Okay, where this Latin indices we are using only for spatial part. Okay, all right. Now, what about eta 0? If you look at eta 0 is equal to dx0 by d tau. Am I right? Dx0 by d tau. And what was x0? X0, we gave the name x0 for ct. Am I right? X mu is equal to x0 comma x vector, or x0 comma xi. All right, that's equal to ct comma usual x1 comma x2 comma x3. All right, or x comma y comma z, let's call it as. Am I right? So x mu is x0 is ct, so we use it here. This is d of ct. All right, and what's d tau? We already noticed that d tau is equal to dt multiplied by square root of 1 minus v square by c square. All right, correct? Yeah.
Okay.
Yeah. So if you have got dt here, so this is simply c divided by square root of 1 minus v square by c square, or simply you can write it as gamma c. Okay. So the zeroth component, or the time component of the for velocity is gamma c. All right. Let's also look at the spatial part. Now eta I you can write it as dxi by dt. Okay, that's equal to dxi divided by d tau. So this is dxi divided by dt square root of 1 minus v square by c square. But dx by dt is the usual velocity, usual tree velocity. Am I right? So this is equal to, we can write it as ui. This is the usual normal velocity that we talk about. Okay, divided by square root of 1 minus v square by c square. You can write it as gamma ui. All right, this is just the usual velocity dx by dt. Okay, so it's related to the usual velocity by this gamma. Okay, so we have got eta. Eta is the for vector, and its components are like this. Eta 0 is gamma c, and these are gamma ui. Is this clear?
Yes.
Okay. Now,
ഫോർ കമ്പോണൻസ് ഉള്ളതുകൊണ്ടാണ് സാറേ ഇതിനെ ഫോർ വെലോസിറ്റി അങ്ങനെ വിളിക്കുന്നത്?
അതെ, ഫോർ കമ്പോണൻസ് മാത്രം പോരാ, ഫോർ കമ്പോണൻസ് ഈ ലോറൻസ് ട്രാൻസ്ഫോർമേഷൻ മാട്രിക്സ് അനുസരിച്ച് ട്രാൻസ്ഫോം ആവും കൂടെ വേണം.
Okay.
It should have four components. If it needs to be a vector, actually a vector is a relativistically invariant object. Okay, I mean it's a coordinate independent concept, but we are calling the components as the vectors. All right, just like if you have r vector equal to xi plus yj plus zk, this is a position vector, right? Yeah, this vector itself is actually invariant because it refers to a point in space. Okay? But when you change the coordinate system, this x, y, and z can change. Am I right? because depending on a coordinate system, what you call x, y, and z will change. Okay, but the vector itself is invariant because the basis also changes. Okay? But for all practical purposes, we can just take these components and call them as a vector. That's what we are doing here. Okay, you just have to remember that vector itself. So this components we can take and call it as a vector. This is the thing that we are using here. So this x, y, z we can call a vector 3 vector. A 3 vector. This is called a 3 vector. 3 vector is a collection of 3 numbers which transforms in a specific way under rotations. Okay, that's a good definition for 3 vectors. Right. So we usually say it has position. I mean it has magnitude and direction, etc. But a better definition is to look. There's a rotation matrix. We are aware that there's a rotation matrix. Okay. So if you have got 3 numbers which transform in a specific way under rotations, okay, then we call it as a 3 vector. In the same way, the 4 vector is a collection of 4 components. Okay, x0, for example, it could be a0, a1, a2, a3. Okay, it's a collection of 4 numbers. That's why we call it as 4 vector, because now we have got an extra time part. We are talking about vectors in space time. Okay, now what's the definition? This cannot be any 4 numbers. These are 4 numbers which transforms under the Lorentz transformation matrix. Okay, sorry, is this clear? So it has 4 components. It has a time part also, because we are talking about space time. Okay. All right, now it's a good exercise to do this. Okay, what is eta dot eta? Can you do this? What's eta dot eta? The scalar product of the 4 velocity with itself. What is it? It's a good thing. We will be using the scalar product thing usually. So what's the definition of eta dot eta? We know that the scalar product is defined like this. It's eta 0, okay, minus. Am I right? There's a minus between time part and the space part. Okay, eta 0 minus, what is it? Eta 1 minus eta 2 minus eta 3. Am I right? Okay, so eta 0 is this gamma c. So we have got this is equal to this is a problem. Okay, we'll do a small problem here. This can be asked. It's a very important thing. Eta 0 is this gamma c multiplied by gamma c. Am I right? So that is gamma square c square minus this is eta 1 we can write as eta vector dot, yeah, yes, am I right? This is gamma square u square, correct? Because this is gamma u1 gamma square u1 square plus gamma square u2 square plus gamma square u3 square. Okay, so you can take gamma. Is this clear, or should I explain why we have a u square here? U square is simply u vector dot u vector, u1 plus u2 plus u3. Okay, so this is what we call as u square. This is fine, and we have got a gamma here. And then കേട്ടില്ല
സാറ് പറയുന്നത് ബ്രേക്ക് ആയിട്ട് ലാഗ് ചെയ്താ കാണുന്നത്.
ശരിക്ക് കേൾക്കുന്നില്ല സാർ, കട്ട് ചെയ്തിട്ട് കേൾക്കുന്നു.
ബ്രേക്ക് ചെയ്ത്
ആണോ? ഏത് ഭാഗാ മനസ്സിലാകാത്തത്? നെറ്റിന്റെ ഇഷ്യൂ ഉണ്ടാവും ചിലപ്പോൾ, അതുകൊണ്ടാണ് ഞാൻ ഇവിടെ ലോക്ക്ഡൌൺ ആയതുകൊണ്ട് എനിക്ക് വേറെ സ്ഥലത്തേക്ക് പോകാൻ കഴിയുന്നില്ല. അത്
റേഞ്ച് ഫ്ലക്ച്വേഷൻ ആണെന്ന് തോന്നുന്നു സാർ.
ആയിരിക്കും. ഇപ്പൊ ക്ലിയർ ആവുന്നുണ്ടോ?
ഇടയ്ക്ക് ക്ലിയർ ആവും, പിന്നെ അങ്ങ് ബ്രേക്ക് ആയി പോകും.
ഓക്കെ, കാര്യം ബ്രേക്ക് ആകുമ്പോൾ ജസ്റ്റ് ഒന്നുകൂടെ ചോദിച്ചാൽ മതി. ഓക്കെ, ഞാൻ അത് കിട്ടാത്തതേ നിങ്ങൾക്ക് പിക്ക് ചെയ്യാത്ത ജസ്റ്റ് ഒന്നുകൂടെ ചോദിച്ചാൽ ഒന്നുകൂടെ എക്സ്പ്ലെയിൻ ചെയ്യാം. Is this clear? Eta dot eta, we are taking the scalar product of eta dot eta. This means eta mu. Okay, eta dot eta is equal to eta mu, eta nu. Okay, we are using the same for the metric also. So I'll just write it as eta mu. All right. So you need to know how to take a scalar product between two 4 vectors. Okay, so it will have a square for the temporal part minus square of the spatial part. Is this clear?
Okay, sir.
All right. So if you didn't follow, just ask me. Okay, I'll write most of the things here. So this is gamma square multiplied by c square minus u square. Correct? So you can pull this gamma, this c square outside. 1 minus u square by c square. And what's gamma square? What's gamma square? What is gamma square?
1 by root of 1 minus.
Yeah, gamma is 1 by root. So if you take gamma square, it's 1 minus u square by c square. Here we have got a c square and again 1 minus u square by c square. You see that these terms will get cancelled and you get eta dot eta is equal to c square. Eta dot eta is equal to c square. Okay. Now this can be asked, right? Now this c square we get because we used the metric in this form. Eta mu nu is equal to 1 0 0 0. Okay, I'll use a notation here, right? I'll write only the diagonal components. Okay, this means it's the diagonal components of the matrix. Okay, this notation is fine. Eta mu nu has 4 diagonal components. Non-diagonal are 0. So I'm writing only the diagonal components here just to save space. Okay. Now you can also use the other convention, eta mu nu equal to minus 1 comma 1 comma 1 comma 1. In that case, eta dot eta will be equal to minus c square. Right? Eta dot eta will be equal to minus c square. This fine? This can be asked.
Yes.
Okay. Now there's an important thing here. I want you to make a connection. So eta dot eta is what do you say, the scalar product of a vector with itself. So it gives you in a way the magnitude of the vector, right? Right? Magnitude of the 4 vector. Because if you usually have a dot a, can take the square root, a vector dot a vector and take square root, you will get square root of ax square plus ay square plus az square, and that we call as the magnitude, right?
Yes.
So here, if you look at the magnitude of this 4 vector, it is a constant. The magnitude of a 4 vector, this 4 velocity is a constant, which is equal to c. This means that, all right, in the way we define the 4 velocity, there is a sense in which the space-time velocity, the velocity in space-time is a constant for all things. All right, the velocity in space-time, every object travels in space-time. So it's not the velocity, it's the speed, all right? Because we are taking the magnitude. Speed in space-time is a constant. So every object is traveling at the same speed through space-time. Okay, not in space, but in space-time, right? And this concept of velocity is slightly different because we have used a hybrid quantity. We have used dx mu by d tau, this sort of a hybrid quantity, all right? But in some way, everything travels in space-time at the same speed, all right? So if you are traveling more through space, you will be traveling less through time. If you are traveling more through space, you will be traveling less through time. Okay, that's a basic thing. So if you are traveling only through, you can also travel only through time or only through space. Okay, if you are traveling only through time in some coordinates, and this can change. Right. So this is why the speed of light is a constant. It's a constant that's associated to the basic structure of space-time. Right. There's a constant that is built into the basic structure of space-time, and it means that the speed of light is the maximum that can be allowed by space-time. Right. It's because of the structure of space-time can only allow this speed. The structure of space-time says that all objects travel at this speed. Okay, that's the reason why the speed of light is a constant. Light happens to travel at this speed through space. Okay, and if you look at it from the viewpoint of light, the clock of a photon does not tick, for example. Right, for a photon, the clock does not move at all. Time is still. Okay, all right. So that's one thing that can be asked. Okay, is this fine? let's go to the next thing.
Yes.
Now we have got what we are discussing next is the momentum for vector. What we discuss now is the for velocity, okay, or we'll also call this as the for momentum. It's also called the for momentum. Okay, for momentum. Now it's easy to define. If we have got three momentum like this mv, okay, we define p equal to mv vector, right? In the same way, we can look at this quantity. P mu is equal to m multiplied by eta mu, right? If you look at this, you can call this as P mu is equal to m multiplied by eta mu. Okay. Now let's look at the components, and you see that m is a Lorentz invariant quantity. Lorentz invariant. It's called the rest mass. Okay, it's called the rest mass. Okay, we are using only rest mass. We are not using the concept of a relativistic mass at all. That's a useless concept. Okay. Okay. So this is a Lorentz invariant quantity, and eta mu already transforms like a vector. So P mu also transforms like a vector. So it's trivial to show that this transformation property is satisfied by the components of the momentum for vector that we defined here is a legitimate for vector because it transforms according to the Lorentz transformation matrix. Okay, this holds true. Now let's look at the components. Okay, let's look at the components. P mu, or we can write the momentum for vector simply with the P, and the components of them. P mu is equal to P0, comma, we'll write as Pi. Okay, and we know P0 is M eta 0, M eta I, right? And what was eta 0? What was eta 0? Eta 0 was gamma C, am I right? Do you remember that? Eta 0 was gamma C and eta I was gamma U, correct? So this becomes gamma MC and this becomes gamma MUI, right? Or in other words, you can also write it as gamma MC, comma, gamma MU vector. Okay, these are the components of momentum for vector. So this is the spatial part. Okay, we can simply write P0 equal to gamma MC is the time part or the temporal part of the momentum for vector. Okay, and Pi is equal to gamma, P vector is equal to gamma mu vector is the spatial part of the momentum for vector. Okay. All right. Now Einstein identified, all right, what Einstein identified. So his arguments are there, we can read, but we don't need this. Einstein identified P0C as the energy of the particle. Okay, I'll just write it here. This is the temporal part, and we'll just say that Einstein identified P0C as the energy, the total energy of the particle. Okay, the energy of we can say as the relativistic energy. Okay, as the relativistic. Again, this comes from the conservation arguments, because if we demand that energy is conserved, we say that this quantity is conserved, all right? We say that this quantity is conserved. So if you want to make the dimensions correct, you should have gamma, you should have P0C. So P0C is equal to gamma MC square. Okay, P0C is equal to gamma MC square. This is a conserved quantity, and this is what we call as the relativistic energy. All right, it's also called as the relativistic energy. So we see here that the energy, all right, energy is getting a new meaning here. What we called energy and momentum were earlier separate, but now energy is actually more or less constant. All right, energy is actually the time component. It's just one component. It's just one component of a 4 vector. Okay, to be more precise, it's the temporal component or the zeroth component. It's a temporal part of the momentum for vectors, of the momentum for vector. Okay, so this energy, the relativistic energy, is actually the temporal part of the momentum for vector. Or in other words, the temporal part of the momentum for vector is identified as the energy, right, with the c. You just have to multiply it with the c. Okay, so E is equal to, we'll say E is equal to P0C, that's equal to gamma mc square. Okay, important relation. Okay, this is known as the relativistic energy. Okay, now again, I had explained this. The rest energy is the total energy, and we already discussed this thing, but we'll just give it again. The rest energy is the, rest energy is we call it as E0. All right, we'll call the rest energy with what is a subscript 0. So E0 is equal to mc square, because gamma will be 1 when u equal to 0, right? So this is the energy of the particle in its rest frame, the total energy of an object in its rest frame. All right, that's also rest energy, and we say that the mass is actually the energy of an object when it is at rest, right? So this is a new concept here, because Einstein has introduced a new concept called rest energy, which was not there in Newtonian thing. All right, so we can call, in other words, we can call mass as the energy content, okay, of an object. It could be a particle, it could be anything, okay, of an object at rest. So Einstein is saying that even things at rest have energy, and the energy content is given by the mass, or the mass of an object is given by the energy content when it is at rest. Okay, all right. Now we can write the kinetic energy, the relativistic kinetic energy. Kinetic energy, right? Kinetic energy is the energy due to motion alone. So you have to take the total energy and reduce and subtract the rest energy, right? Total energy minus rest energy. Okay, total energy minus rest energy. That is gamma mc square minus mc square. Okay, we can just maybe simplify it a little bit. You can write as mc square into gamma minus 1. Okay, this is the relativistic kinetic energy. Okay, relativistic kinetic. Give me a moment. Okay, are we following?
Yes.
Okay, so are there any questions?
Sir.
എന്തെങ്കിലും ചോദ്യങ്ങളുണ്ടോ? ക്ലിയർ ആയോ? പറഞ്ഞെല്ലാം കറക്റ്റ് ആയിട്ട് കിട്ടിയോ? ഇടയ്ക്ക് കട്ടായി പോയോ?
ഇല്ല, കിട്ടി.
ഓക്കെ,
ഇപ്പൊ ചോദിച്ചത് മാത്രം.
ഇപ്പൊ എല്ലാം കിട്ടിയോന്നാ ചോദിച്ചത്. Now let's look at the spatial part of the momentum for vector. Okay, let's look at the spatial part of the momentum for vector. Okay, so as we said, the spatial part can be written as a vector. It's gamma mu vector. Okay, spatial part of the momentum for vector. Okay, it's gamma mu vector, and this is known as the relativistic momentum. This is known as the relativistic momentum. Why do we choose this quantity as relativistic momentum? Because it has a nice property that you can see that in particle collisions, etc., it's conserved. Okay, all right. So relativistic momentum of an object, the spatial part of the momentum for vector is the relative. We already saw this, all right, but I'm introducing it again in this direction. Okay, the relativistic momentum of an object. This spatial part of the momentum for vector is the relativistic momentum of an object with mass m, and velocity u vector. Okay, so if a part, this is the usual velocity, right? This is the usual velocity dx by dt, okay, or dr vector by dt. This is the usual velocity. So if you have a particle moving with a velocity u vector, the momentum, the relativistic momentum of that object is gamma mu vector. Right? The Newtonian was mu vector. The Newtonian momentum was mu vector, but the relativistic is gamma mu vector, and you see that it has a nice property that when you take v much less than c, okay, it will reduce to this Newtonian momentum, right, or Newtonian momentum. Okay, all right. Now, why do we choose, the main reason to choose this as the momentum and not mu vector? We don't choose mu vector as the relativistic momentum, but we choose gamma mu vector. Okay, why do we choose gamma mu vector? But we see that this definition has to be chosen. This definition has to be chosen. You can see, look at some textbook, there are elaborate arguments. Okay, this definition has to be chosen so that chosen for momentum, so that the law of conservation of momentum, the law of conservation of momentum, the law of conservation of momentum, okay, is consistent with principle of relativity. With principle of relativity. All right. So if you take mu vector, simply mu vector, you'll see that this is not conserved in high energy collisions, but gamma mu vector, if you take gamma mu vector, this has a nice property that this is actually conserved. This is actually conserved. And this also has the nice property that if you take the non-relativistic limit v much less than c, it reduces to the usual mu vector. Okay, so this has all the necessary properties, because we know that in low energies or Newtonian physics, mu vector, p vector is equal to mu vector, is conserved in non-relativistic, right? In non-relativistic, this is already conserved. We have studied this extensively, the conservation of momentum, and there is no external force as acting. The momentum is conserved, and that momentum is mu vector in Newtonian. Okay, but the generalized form is gamma mu vector, and it has nice property that it reduces to the Newtonian momentum when v is much less than c. Okay, so this all this argument suggests that this is a good definition for momentum. Okay, it has all the necessary properties. It's conserved, it reduces to the usual momentum that we are familiar with, and in the non-relativistic limit. Okay, now there's an important fact. Okay, you can call it an experimental fact, but it's also kind of a law of physics. Okay, experimental fact. All right, what's this experimental fact? It is this: in every closed system, the total E and P defined here are conserved. All right, in every closed system, the total E, energy, and momentum, P vector, defined here, the total, all right, the total E and P defined here are conserved. Okay, now this you should know that the conservation of energy and momentum are actually experimental facts. Okay, there are no experiments that have violated this. That's the reason why we believe it. Okay, and you know that it has a deep connection with symmetry, right? So you might have you may remember from our Noether theorem that we discussed earlier, conservation of energy. Conservation of energy corresponds to what do you say, homogeneity of time, am I right? Or invariance under what do you say, the laws of physics are invariant under time translation. All right, homogeneity of time. Okay, and conservation of momentum we have associated with homogeneity in space. It doesn't matter where your system is. Okay, it's here or there, the physics will be the same. Okay, together now we are saying that we have combined this energy and momentum into one 4 vector. All right, so we can simply say the concept, the 4 vector, we can simply say together the conservation of energy and momentum together. We can say that the 4 momentum is conserved. The 4 momentum is conserved. Okay, 4 momentum is conserved, and the corresponding symmetry we can simply call as the homogeneity of space-time. Homogeneity of space-time. It doesn't matter at which space-time point you are, the laws of physics will remain the same. Okay, so this we can call the homogeneity of space-time, or it's also known as you can also call it as translation, the translation invariance. Okay, translation in space-time is a symmetry. Okay, all right. So it's easy to see this. All right, if you take dA square equal to c square dt square minus dr vector square. All right, what do you mean by translation? By a space-time translation, you are changing by a constant amount. Okay, you are changing time by a constant amount and space by a constant amount. But since we have a d here, all right, since we have a d here, d of that constant amount is 0. So this dA square, or this interval, remains invariant under translations, because translation means you are just adding a constant. All right, you're just adding a constant, right? Because we have a derivative here, this remains invariant. So we also said this is invariant under Lorentz boosts. Okay, Lorentz boost. We also saw that this is invariant under rotations, spatial rotations. Why? Okay, spatial rotation does not affect time. Okay, spatial rotation does not affect time, it affects only the space. But let me write it clearly here: c square dt square minus dr vector square. Okay, so if you make a spatial rotation between x, y, and z, it won't affect the time, it will affect only this, and this remains invariant under rotations, right? Because dr vector square is the length of an object. Am I right? So this also remains invariant under spatial rotations. All right. So this is the complete set of important symmetries of this interval, a space-time interval. Right. And together this is known as a Poincare group. Poincare group. If you are, you might be looking at the group theory in some context, and this is what we mean by Poincare group. Right. I'm not going in detail into this Poincare group. I'll just tell you this because it remains invariant under translations. How many translations are there? Possible translations are there. You can make a time translation. You can make a translation along the x direction. You can also make a translation along y direction or z direction. Right. So there are totally 4 parameters for translation. Right. There are 4 possible parameters for translation. What about spatial rotations? There are 3 possible spatial rotations. Am I right? You can rotate about independent, I mean, right? You can rotate about x-axis, y-axis, or z-axis. So there are 3 here, 3 rotations. And how many boosts are there? Independent. You can boost along the x direction, y direction, or z direction. There are 3 possible boosts. Okay. So this is a 10 parameter group. This is just an information. The Poincare group is a 10 parameter group. It's a group of symmetries of the space-time interval. Or we can simply say the symmetry group, a complete symmetry group for dA square is the Poincare group. Okay, it's a 10 parameter group. 10 parameter because there are 4 translations. Okay, 3 rotations and 3 boosts. Okay, 3. I'll write it like this: 4 translations. We are meaning independent. All right, so we'll have 4 independent parameters for translations, 3 rotations, and 3 boosts. Okay, so it's a 10 parameter group. Okay, I don't know, when you study mathematical physics, you may come across this or you may not. Okay, but it's an example for a group. All right. And again, we see the important point that mass is not conserved. Mass is not conserved. Okay, energy is conserved, momentum is conserved, but mass is generally not conserved. Okay. Now here it may be a bit confusing at first, because just before some time I said mass is invariant. Okay, so there are two words that we are using which seems to have the same meaning, but you have to distinguish between. All right, we have got invariant quantities. We have got invariant quantities. Okay, we have got invariant quantities, and we have got conserved quantities. We also have conserved quantities. Okay, so if you take, for example, the energy, okay, invariant, by invariant we mean that when you go from one frame to another, it does not change, its value does not change. So if you take energy, you'll see that it's not invariant, but it is conserved, energy is conserved. All right, if you take the momentum, the through momentum, you see that it's not invariant, but it is conserved. All right, if you take the mass, you see that it is invariant, but it's not conserved. Okay, because mass and energy, some of the mass can go as energy and some of the energy can materialize as mass. Okay, in particle interactions, for example. So you see that mass is invariant but not conserved. Now this can be asked in which of the following is true kind of question. All right. Okay, this is possible. I think it has been asked, if not for NET, for some other competitive exam. Which of the following statement is true? Okay, it can ask both energy and momentum are invariant and conserved. Mass is invariant and conserved. All right, something like that. So it's and if you look at charge, okay, electric charge, you'll say that it's invariant and conserved. All right, it's invariant and conserved. All right, fine. Are you still following?
Yes, sir.
All right. Should we stop here or should we just look into one more thing? Do you have time?
So stop it.
Okay, so we'll stop here. Okay, we'll continue in the next class. Next class, I'll show you why we say the mass is invariant. Okay, in the next class, I'll show you why we say mass is an invariant quantity. All right, because we know that scalar products are invariant. I'll show you that the mass is related to a scalar product of four vectors. All right, so that's the reason why we call. That's one reason why we can. That's one way we can show that mass is actually an invariant quantity. Okay, so we'll do that in the next class. Thank you. Are there any questions?
Okay, sir. Thank you.